like I say, there's several methods to approach solving these problems, but the one I promote the most, because in my humble opinion, it's less steps once you understand the idea of the mole concept. So the rule is convert data, I should say, given to moles. And then convert to needed dimension at the end of problem. So this is the idea I'm trying to get across to you, because in my humble opinion it's the easiest way to go. You can break down just about any problem that involves moles much easier than you can grams or particles or gas volumes or anything else like that. You can get them to moles. To me, it's much simpler and easier to see through the problem, no matter how complex it is. Now, some of the things that you need to know: if the data is given as moles, just solved by ratio. If that's what they're asking for, mole-mole relationships. If they're giving you grams, then moles is equal to mass in grams divided by the formula weight of the substance. That'll get you to moles in that case. If you're given in gas volumes, moles at STP is volume in liters divided by 22.4 liters per mole. Okay? And those will get you into the moles. If you have solution data, if you recall from the lecture, when you have solution data, it will have two data points or data items together always. And that's molarity, that is a concentration term, and a volume term expressed in whatever is given. But the moles, if you're in solution data, is molarity times volume in liters. You can see that, I'm sorry. So these are very important data streams that you need to recognize as you read one of the problems. And then you extract that data and say, what can I do with this to get to moles? And then, of course, you either ask to write and balance an equation, or the equation is given to you. Then you just go by ratio. If 2 gives you 1, then 5 gives you X, and just work from that. Okay, let's see if there's something else. Okay. Consider the combustion reaction is methane plus oxygen, gas, molecular oxygen, always goes to CO2 gas, plus 2 moles of water. I call it new water in the context if it's in a solution. So. What is the theoretical yield of CO2 if 0.2 mole of methane, you're given 0.20 mole of methane, is mixed with 0.30 mole of CO2? And so we're looking at the theoretical yield in moles. Okay, if you don't understand why I'm specifying theoretical yield by definition is the values determined from stoichiometry of the equation. They're exact in a perfect world. Then there is actual yield, which is laboratory yield, some people call it, and that's the real value that you get out of a given reaction. And of course, you'll see that as part of the percent yield that you'll need to work on one of the problems. Okay, so since everything's in moles, all we need to do is determine which one is the limiting reagent. So how do we do that? Well, you look at the coefficients of the standard equation. You've reduced it to the smallest whole number ratio. If you divide these by the respective coefficients, I'll put that in there just as a notation. Divide by the respective coefficients, the smaller of the numbers in your computation will be the limiting reagent. So this ratio is 0.15 and this ratio is 0.20. So the smaller value is the limiting reagent or reactant. Now, while this is a technique and there is logic in the reasons I'm doing it, but it's not important in just determining the limiting reagent. What you need to remember is you must work problems from the mole values that you have up here. And base it on the limiting reagent. So when we look at this relationship, we see that the limiting reagent is the 0.15 from the calculation, but we must work our problem from 0.3. So 2 gives us 1, 0.3 gives us x. Well, we see simply that CO2 is a smaller number on the coefficient by half. So if I divide that by 2, I would get the 0.15 anyway. Yeah, but that's not how you answer this problem. So we can say that limiting reagent is the CO2. Then we set up our problem. 2 moles O2 goes to 1 mole of CO2. Then you can see, then you ask yourself 0.30 mole O2 goes to X, and work through that ratio, and we see it is simply 2 over 0.3 is equal to 1 over X, and that's 2X equals 0.13, and X equals 0.30 over 2 mole, or 0.15 mole theoretical yield. ET. And our answer choices, that would look like B choice in that collection. So what I've outlined here is convert to moles. Okay, once you get moles, it's already given. You divide by respective coefficient to find the limiting reagent, and then work the problem based on that limiting reagent. Okay, number 2 says, what is the yield of NO2 gas when 28 grams of N2 gas react with 64 grams of O2 gas in the following reaction? Okay, so we have 28 grams of nitrogen, molecular nitrogen, right there, and then we have 64 grams of molecular oxygen. Now what's the rule? Convert to moles. And since this is grams, how do we get there? Divide by formula weight. Okay? So nitrogen is 1414 or 28 itself, 28 grams per mole. And oxygen is 16 per atom, so that is 32 grams per mole. And so the computation is 2 moles of the O2 is the reactant, and 1 mole of molecular nitrogen. Well, this is what we call a stoichiometric exact calculation, meaning that moles equal moles. Moles in the reactant side conform to the standard equation. So the question is how much, let me see, they want it in grams? Yes. How many grams of the NO2? Well, looking at this, 1 to 2 gives you 2. Then, of course, this combination being matching the equation is going to give you 2 moles of NO2. Well, the formula weight of this, 16, 16, 32, 42, 48. So this is times 48 grams per mole and 96 grams NO2 gas. And again, that's a theoretical yield. So if you were having to calculate percent yield, the problem would have had to give you, well, the laboratory yield was, say, 90 grams. And you'd 90 over 96, it'd be your ratio times 100. Wow, did I say 90? Why did I write 92? Okay, you're given ethylene and oxygen producing C2H4O2 is balanced to the lowest whole number ratio, which means you assume that reaction is at STP. And I wrote it in the problem, so you'll know that. But a lot of times they'll give you the data, and they won't mention that that's an STP. And if there's nothing else given in the problem, then you assume STP condition 0 degrees Celsius, 298 Kelvin, and 1 atmosphere pressure. Right there. So you kind of have to read into the problem relative to, well, what are the conditions? If you've given me volume, I have to start somewhere. You assume that the equation is given at STP conditions, 0 degrees and 1 atmosphere. Now, if they want some different non-standard conditions, you still have to start at the standard conditions and then make conversions. Well, I haven't taught you that yet in terms of the gas laws. Charles law, Boyle's law, combination of those and so forth. Okay, so what we need here is the theoretical yield, in that percent yield is the actual yield divided by theoretical yield 100%. So we have the actual yield here, so we need to get the theoretical. Well, that comes from calculation using the stoichiometry of the equation. Now, we'll take the, we need the moles of the C2H4, which is 56 grams of that compound, divided by its formula weight. So that's 12, 12, 24, 5, 6, 7, 28. All right, that's 2 moles. And then we're given 22.4 liters O2 at STP. Well, I wrote it in there for your benefit. Well, that represents 1 mole of O2 gas. And so when you set up your problem, you set it up relative to 2 moles of ethylene and 1 mole of molecular oxygen. So we'll just redo it down here. Move it up a little bit. I'll leave the states. They're all gases. So we're putting these into the equation. We have 2 moles, 1 mole, and so that is a stoichiometrically perfect calculation. 2 and 1, 2 and 1, so we get 2 moles theoretical yield. Okay, now in order to do the percent yield, we need it in grams because the actual yield was 65.12. Well, this one has, let's see, has a formula weight of 88. No, you know, it's, is it? Yeah. No, that's a theoretical yield. 44, sorry. So, times 44 grams per mole, and that's 88 grams theoretical yield. So now we're able to apply this equation. Just move this up here to get that percent yield. Is now 65.12. Wish I could keep it all on the page. Let me try. Two grams, and theoretical should be 88.00 grams times 100%. What did I get out of that? 74% yield. Weight ratio yield. And that, my friends, is B choice. And those keep you score. Okay, so very, very important setup on the types of problems here, and trying to get through some of these. Okay, in this reaction, you have 3 moles of hydrogen gas mixed with 3 moles of nitrogen to produce whatever moles of ammonia. Now the question is, how many moles of N2, which would be the excess, and hydrogen being the limiting reagent. How do we know that? Well, if I divide 3 by 1, it gives me a 3, and 3 by 3 gives me a 1. The lower number is your limiting reagent. Right there. So how much is the excess of nitrogen? Well, in the equation, it's a 3-to-1 reaction ratio. So we're going to use up all of the hydrogen. Okay, and that's the first thing you need to recognize, which one goes away. Well, it's always the limiting reagent, then the reaction stops right there. Now, in the process, how much of the nitrogen will you use? Well, if we have all of this used, then I'm only going to use 1 mole of N2 gas. So over here, we'll only use 1 mole of N2 gas by equation reaction ratio. So if I've got 3 moles given in the mixture that we started, and I use 1, then excess N2 gas will be 3 moles that you started with minus the 1 mole that was used, and that of course gives you 2 moles N2 gas in excess. And so that is B choice in that selection. You will see this kind of problem, and it will be very important in determining excesses to determine what the alkalinity or acidity of solutions are. And that is very important that you determine how to calculate the excesses from a reaction. Because, of course, the limiting reagent's gone. It's not going to affect pH. But if you have some base left over or acid left over, of course it's going to affect pH. So you need to know how to calculate how much, so you can calculate the exact pHs and stuff like that, which we will get to in due time. Okay, now, when you see this, hopefully you remember talking about the solution phase data. Well, of course, there's always 2 data items in a solution phase that you need to calculate moles, which is then related to the equation solved by ratio, and if they need a volume or molarity or whatever else, and we'll do that today. You'll see how this problem applies to today's work, and you can calculate how much solutes is remaining in a solution or an unknown concentration. And okay, so you're given 20 milliliters of a 0.19 molar sodium hydroxide aqueous solution reacting with 30 milliliters of a 0.1267 molar hydrochloric acid solution, like that. In the above reaction, what is the limiting reagent or reactant, and what is the concentration of the compound in excess? Okay, so we need to convert to moles and then divide by the respective coefficients. Well, the respective coefficients in this reaction, which is NaOH plus HCl, goes to NaCl plus H2O, just an acid-base double replacement reaction. So which one of these will be the limiting reagent? Well, they got equal coefficient, so you really don't have to do the division step. Whoever's the smallest number of moles out of this calculation is the limiting reagent. It will go away first, and then you'll have the other one left over in excess. So to get to moles, from solution data, we remember it's molarity given times volume expressed in liters. So what we want to do is apply this first to change the data and set it up as a multiplication to generate moles. So here's a 20 milliliters. Well, move the decimal 3 places to the left and you can convert to liters. So that's 0.020 liters times the molarity, 0.19. The way I suggest doing this is, you know, this is liters and your molarity. I just put moles here. And then when you calculate it for the next row down here, you just multiply those and put it right there, and you'll have your moles of your sodium hydroxide plus 0.030 times 0.1267 molar gives you moles of the hydrochloric acid, like that. So when these are multiplied together, when we multiply these two together, 0.02 times 0.19, I get 0038. Well, that's moles of sodium hydroxide in the reaction. And then 0.03 times 0.1267 gives you the same number, 0.0038 moles. So the moles of sodium hydroxide equals the moles of hydrochloric acid. But what does that mean? Well, the only thing remaining in the system after that reaction is completed, when there is no limiting reagent. Only sodium chloride is left in the reaction solution, plus any new water that's generated, and it's really not taken into account, considering there's also the solvent. So when we have this matching equal volumes of equal molar solutions, always completely neutralized. That means all of the acid and all of the base is gone. The only thing you have in the reaction solution is the salt. Acid plus base gives salt and weak electrolyte, or water in this case. So this would give you 0.0038 mole of sodium chloride. See, it's also a 1:1:1 reaction ratio in this reaction. And so you get 0.0038 mole of sodium chloride remain only stops like that. And of course there is no limiting reactant. And that's D choice in that collection. There is no limiting reactant, as both reactants are equal moles in a 1:1 reaction ratio. Neither compound reactant is in excess. Only sodium chloride and new water remain in an amount of 0.076 molar of each. Now, this is moles. Remember what I told you, moles is not molarity. And you'll be asked to calculate a final concentration in moles. that is the concentration of sodium chloride. The brackets that I'm showing in symbology here are classic in their use as indicators of molar concentrations. Very important little footnote in your learning curve. So how do you get to molarity? What is molarity defined as? You recall from our talking of solution? Moles per liter. Yes? Okay, so molarity is moles of the NaCl over the liter's total volume of final solution. Well, the moles is 0.0038 because it'd be 1 to 1, and that's all is going to be produced. It's not 2 times 0038. The reaction says 1 to 1 to 1. That's it. So we have 0.0038 mole of the sodium chloride. Now, what's the total volume? You poured 30 milliliters and 20 milliliters together, giving you 50 milliliters final volume. Well, that has to be converted to liters, so that's 0.050 liter solution. So it's moles per liter solution. And so the outcome of this is 0.076, was it 076? Yeah. 076 molar in sodium chloride. Very important computation. And it shows you the steps as you go through. You're given solution data. It kind of looks busy, of course. But now you should say, okay, that's solution data. I need to get it to moles. Well, once you get here, it's very simple to see it's a 1 to 1, and it's gone. So only thing remaining is the sodium chloride, and it's a 1 to 1 to 1 also. And so the outcome is 0.0038 mole sodium chloride in solution, and that total volume of solution is 50 mils, or 0.05 liter. And you can calculate the molar concentration from that definition right here. So what I've tried to do is give you a cross-section of the problems that you'll see coming at you on exam day. Okay?